Okay. Yeah, so that's our basic idea is we want the motor to respond only to the DC component and to basically not react to the higher harmonics, which we said is the act of filtering. All right, so what we did is to do that, I said last time we basically wanted to figure out the transfer function of the motor, H of omega. So the input in this case is the voltage V sub A, and the output is the speed. And we went through and we said, all right, what that means in this particular case, and I'm going to actually jump ahead here in my slides for a second. So in the case of the DC motor, in problem one, I have you guys figure out the differential equations, or I give you the differential equations. I said there's two of them, right? There's basically one where I have the electrical equation for this guy. So if I did a KVL around this loop, I have V sub A equals IA RA plus LA DIA by dt plus K omega of t. So this thing here I talked about last time. This is basically a dependent source inside the motor. All right. So you'll learn in later classes how to model this thing, but basically what it's saying is this is a circuit model for the motor. This isn't this V sub A is basically that H bridge or whatever that gets connected to this thing. All right. So basically what's inside the motor is pretty simple. It's just some wire and then this voltage source, right? But the voltage source is basically it's a result of the physics going on inside the machine. Basically a result of Faraday's law. All right. And it's a model for what that system is actually doing. So what I said is you had this differential equation, and then you had essentially a mechanical version, which is this J d omega dt, which is KIA of t minus beta omega of t. For some reason I can't draw my omegas very open. All right. So let's see if you guys remember from the other day. What is this expression? Do you guys remember where I came up with that mechanical expression? Anybody? One of Newton's laws. So you got three choices. Which one of Newton's laws was that supposedly? See if you guys remember.
Law?
Which one?
Second law?
Yeah, second law. Basically, it's the net torque. We're saying this here is the net torque on the machine. We're saying the net torque equals the moment of inertia times the rate of change of speed, which is it linearly, right? You think of Newton's second law as F equals ma. The net force equals mass times acceleration. Rotationally, it's that. So one of the things that we said, the reason I talked about this real quick is I said last time, when I have a system like this, right? Figuring out the H of omega means I start from a differential equation, and from the differential equation, I get my H of omega. So for the motor problem, just to be clear, what you guys are going to have to do in problem one is you take the Fourier transform of both sides of this equation, the Fourier transform both sides of this equation, and then you combine those into um, one transfer function. And you should get an expression which is basically omega, my output, is equal to H of omega times VA of omega. All right, that will be what you need to figure out. Somehow you'll take the two Fourier transforms that come from each of those expressions and combine them, right? Combining them is simple. It's just algebra, right? What you'll probably want to do is to basically take the Fourier transform you get from the first equation, solve for I sub A in terms of VA and omega, and plug that into the other differential equation, and then you'll have it. Okay. All right, that's basically the way it works. And I got to be clear about that. You're not plugging into the differential equation. You take the Fourier transform of both of those, and then you solve for the Fourier transforms like this. It's a very simple thing to do once you know how to get the Fourier transform. Okay. All right. So the other day we basically tried this I gave you sort of a similar problem. All right. And I wanted to just recap that. So basically I said I had this circuit here, and I'm applying this voltage here. And what I want to have happen is I want V out of T to be a constant. All right. I want it to simply be, um, let's say I want it to simply be 2.5 volts, right? So for the way I have this set up right here, I could have that output be simply 2.5 volts if I choose the values, if I choose this frequency T or the period T, if I choose that properly, then I can ensure that the output voltage, the voltage across the capacitor, will just be 2.5 volts. And I said tau, which is RC, is 0.5 seconds. So you guys should know basically if I have this thing, the differential equation becomes this. Okay. So if I have that differential equation, I want to figure out what h of omega is going to be, right? So if our goal was basically just to see 2.5 volts at the output, right? Let me ask you this. What would be the Fourier transform V out of omega? What's the Fourier transform of 2.5 volts if I just have a constant like that?
Is it just a DC term?
It's just a DC term, yeah. So basically it's just an impulse right here, right? At 2.5. So if I looked at the Fourier transform of Vn, right, it's got all these other terms in it. So what we talked about the other day is that basically if I'm doing a design problem like this, what I and the relationship between V out and Vn is like that, right? So that's how we relate their magnitudes. What I said is I would like for h of omega to have a magnitude of 1, very close to 0. So the only thing that comes out of the filter is a constant. If that's the case, then in the time domain, if I'm applying this voltage here, then the output voltage will look like this one right here. It'll look like just a flat value. All right, so the thing we got to do is so our goal basically is sort of 3 steps, right? This is the relationship we have between the transforms of the input and the output. If h of omega looks like this, remember, you're just multiplying this guy and this guy together to get this. All right. So you're basically so this guy would be 0 where all those other impulses are, so that all of those other impulses basically disappear from the situation. All right. So if I figure out, let's just real quick, we walked through this the other day, but just as a reminder, all right. So let's say I have this differential equation. I want you guys to help me out to figure out the Fourier transform. Oops. Tau dv out by dt plus v out. Okay. All right. So how do I get to the h of omega from this? I take the Fourier transform of both sides, right? So what happens when I take the Fourier transform of both sides of this thing? What do I do with the v in of t? What do I replace that with? So what do I do with the left side? That should be the easy side. If I have a v in of t, I replace that with what? I heard something there real quick.
Do you replace it by Vn of omega?
Yep, v in of omega. And what do I do with the other side then? What do I do with the d by dt?
You multiply by j omega, I think.
So d by dt becomes j omega. Yep. And then all the v outs become v out of omega. And this is not a differential result. This is just algebra. That's what I'm saying. Like when you have the motor, you can just combine the two that you get from the two differential equations, right? So here, I just factor out the v out of omega. And I have j omega tau plus 1. So basically, if I rearrange, I have v out of omega equals 1 over j omega tau plus 1 times Vn of omega, like that. Okay. So this is my h of omega. All right. So that's what we worked out last time, right? So basically, my h of omega in this particular, so our goal, all right, is basically we're looking at trying to remove all of these terms in Vn of omega. We want to make sure our h of omega is basically zero out here where the harmonics are. And this is our actual h of omega, right? Our actual h of omega is apparently this, right? Now, what I said last time is if I look at this, if I take the magnitude of it, right? If I take the magnitude of this whole thing, the magnitude of that is only going to be zero if omega goes to infinity, right? If omega goes to infinity, then I'm basically going to have 1 over a large number, which is going to be 0. This guy is never going to be fully equal to 0. And for any real system, you never have these filters basically have a 0 value, right? What we ended up doing is we said we needed to have some design constraints, right? So last time, basically what I said is you can only do this approximately, right? So my goal, I said, my design goal was to basically have my filter be 0 out here with its magnitude. I can't do that. What I can do is I can make sure that my filter magnitude is small, right? And so what I did was I said, I want to try to get the output to be approximately constant. So I said I wanted to choose a fundamental frequency, omega naught, which is equal to, right, 2 pi over t. I want to choose that value so the amplitude of the sine wave at the fundamental frequency is less than 5% of the DC value. All right, so what does that mean, right? So what we talked about last time was I basically said, if I look at my Vn of omega, right? In particular, if I look at my Vn magnitude at omega naught, right? That's going to be essentially, if you look at it, it's whatever the value of alpha 1 is for Vn, okay? And I gave the example last time. I said if it was a 50-50 square wave, right? So like this guy. So 50-50 is high 50% of the time, low 50% of the time. Probably should have written that value down, but this guy works out to be, I think, something like negative j times 1.5 or something along those lines, right? And so what we do, and so the I guess magnitude wise, it's about 1.5. I'll say it that way, right? Since I'm talking magnitudes. So if I'm talking about, what's the sine wave in that particular thing? So if I looked at Vn at the fundamental, that would basically be 2 times 1.5 times cosine omega naught t plus some angle, right? And I don't really care what the angle is. What I'm caring about is the magnitude. So that's the magnitude of Vn. What I'm saying is I want to choose the fundamental frequency. So choose the value of omega naught. So the amplitude of the sine wave at the fundamental frequency in the output is less than 5% of the DC value. So that means that what I want is for V out of omega at omega, so specifically at omega naught, I want that to be less than 5% of the DC value, which is 2.5, right? And because V out is equal to the magnitude of H times the magnitude of Vn, we said this creates a constraint on the magnitude of V out at that particular frequency, right? So basically what we need to do is we know this value, right? So it's about 1.5. That creates a constraint on what the magnitude of H of omega naught must be. Basically, the magnitude of H at that frequency must be less than basically, so it works out to be, so 0.05 times like this, right? 0.05 times 2.5, right? that value there. Let's just do it here. All right. So here's what works out to be, right? So if we do 0.05 times 2.5, that works out to be essentially 0.0625. So the constraint that we have is basically that. So what I do is I put in the specific value. So I said it was about 1.5. The magnitude of Vn at omega naught is 1.5915, right? So I basically just rearrange this expression here to see that the magnitude of H at the fundamental frequency has to be less than 0.0393. So what I have to do is I have to choose this value of omega naught so that this is true. All right. That was the goal that we had. So basically what we did last time is I basically said, all right, well, my H of omega is equal to 1 over J omega tau plus 1. All right, so that's what it is. And so tau I defined previously and said tau was 0.5 seconds. So what I did here was I made a graph of the magnitude. Now notice what I did. I created an omega vector, right, which went from 0 to 100 hertz, right? So omega goes from 0 to 2 pi 100. And my H is this. So notice that I have this dot divide in here, right? So I basically do 1 dot divide over j omega tau plus 1, like that. So and I have to do the dot divide because omega is a vector, right? And then I plotted the magnitude. And I said, this is what we see, all right? We want the magnitude to be less than 0.0393. I don't know where that is. That's somewhere out here. All right. So it's a little hard to actually see that particular point. So what I said is because this thing ends up being so squished up, we tend to want to use a logarithmic scale. And this is kind of where we ended last time. Right. So I went through this argument here where I'm using log base 10. And I basically said, okay, if I take a bunch of numbers that are powers of 10, what do their logs look like? So basically what I'm doing here is, right, this guy is log base 10 of 10 to the third. So I went through this thing last time, so if I take the log of a number, so if I take the log base 10 of 10 to the nth power, that becomes n times log 10 to the 10, which the log of log 10 is 1. So this becomes n. So if you look at this, basically on the log scale, as I go from 1,000 to 100 to 10 to 1 to 0.1 to 0.01, I'm basically going through here 10 to the third, 10 squared, 10, 10 to the 0, 10 to the minus 1, 10 to the minus 2. So basically on a logarithmic scale, it just goes from 3, 2, 1, 0, -1, -2. So essentially what that means is if I'm looking at this scale here, so if I'm looking at a linear scale for my frequencies, as I go from 0 to 10 to 100 to 1,000, basically on a log scale, what would that look like? Well, so 10 would be at 1 on a log scale. 100 would be at, so this would be 1, this would be 2, this would be 3, 4, whatever. This corresponds to 100. This corresponds to 1,000. This corresponds to 10,000. This corresponds to 100,000, like that. So it basically gives us a way to kind of zoom in on things to see what's happening a little bit better if we look at this thing on a logarithmic scale. So last time, I basically kind of ended with this. And so I want to take a closer look at this expression that I've created here. What I did is I said, you actually, by convention, when we look at these things, what we tend to do is we look at both the log of the magnitude of the transfer function, as well as plotting it on a logarithmic frequency scale. So what I have here is I'm plotting 20 times log base 10 of the magnitude of h of omega. All right, so what I did here was I created essentially an omega vector. I called it omega 2 because in my code I basically had two different values for omega. But if you look, I used this function called log space here to create essentially a logarithmic set of frequencies. So if I look at this for a second, log space, that command, log space, -2 to 1000. All right. What that does is it basically creates a set of frequencies, creates 1,000 points between 10 to the -2 and 10 to the 2, right? And then it creates 1,000 points between those two endpoints. And then basically what I did is I used this what's called semi-log x command. If I do the semi-log x command, it makes sure to plot this on a logarithmic scale. So let's see how you can see that I have the logarithmic scale, right? If you look at this here, you see that here's 10 to the -2. So basically this is -2, -1, 0, 1, 2, 3, right? So you notice those basically those factors of 10 in frequency are basically linearly separated from each other when I plot them on a logarithmic scale. So you need to use the semi-log command, and then what I'm plotting is 20 times log 10 of the magnitude of h. Now notice that I did log 10. I know you guys are used to typing log into a calculator. All right, but it's actually log 10 that you have to use when you're in MATLAB. I said using log. Log doesn't work. All right. Log is actually the ln command in MATLAB. Okay. Any questions about what's there? Okay. All right. I have a feeling you guys will struggle with that a little bit as you go through the project, right? You're going to have to do this basically. You have to, in problems 2 and problems 3, you're going to be generating these sorts of plots. All right. I do recommend that you try to do it. We've only got one more class that's left. I do recommend that you try to do it before class next Tuesday, so that when you come to class on Tuesday, you'll have some pretty focused questions to be able to ask me about the project. All right. So basically this is the graph that we had. All right. And so what I do here is I basically say, all right, I look at this graph, and we said the constraint that we had, all right, the constraint that we had was that we wanted to choose h of omega naught to be less than 0.0393. That was the constraint we had. All right, so because this graph is done on this scale here, right? This we call decibel scale. What I do is I take 20 log 10 of, let's say, 0.0393, right? Figure out what that is, all right? That works out to be somewhere around about -28 dB, right? So if I calculate that, it's about -28 or so. So what I did was I went down and I found something less than that. All right. So in other words, more negative than that. When I take the logarithm, right? That's when I take the log of a number that's less than 1, right? It just becomes a very negative value. So when I take 20 log of this number, it becomes 0.0393. So basically on the log scale, it's saying if I choose anything more negative than -28, then the number I'm taking the logarithm of is getting closer to 0. So basically, in this case, what I did was I said, well, what happens if I go out here to this particular point, 56.3843? At that point, I see that, so it says y value is -29.008. The y value here is 20 log 10 of the magnitude, right? So if I do that at that particular frequency, right? The magnitude is -29 decibels, which means that it's basically less than 0.0393. That's essentially what we're doing here. So what you do in problem 3 is you say, okay, well, if I choose omega naught to be that value, right, then I can choose the value of t that I want from that. So what you end up doing in problem 3 basically is you go through a very similar exercise, right? You basically choose a frequency just like I did, right? So I give you a constraint. You have to basically translate that constraint into an equation like this, make this graph, and then choose a frequency. And you got to make sure that you choose a frequency such that it's, if you define a particular threshold, that you go essentially making sure that on the dB scale you're more negative than that constraint. Okay, that's going to be because the log of a number less than 1 is a negative value, and the smaller that number gets, right, the closer, the more negative that number is going to become. All right, so what you're going to do is you're going to use this approach. You're going to choose a t value, and then what you're going to do is you're going to apply that to the motor. And so what you're going to do is you are going to essentially, in the case of that particular problem, what you're going to do is you're going to choose the value of t, and then you're going to apply that to the motor, and you have the equations for the motor from problem 1, okay? And then you're going to see what the motor does as a result. So you're going to track what its speed does. All right, so essentially in this particular case, in my example here, I'm doing this for an RC circuit, right? So my constraint was that I wanted the output to be approximately constant, and I wanted to choose the frequency omega naught, so the amplitude of the sine wave at that frequency would be less than 5% of the DC value, which meant that it was going to be less than 5% of 2.5 or 0.0625 was what we came up with. All right. All right, so what we do is I basically to verify that this actually works. What I did was I actually chose the value. I took that omega naught, determined what t it corresponds to, and then I basically simulated this circuit, meaning I solved the equation numerically by giving it this particular input here with that value of t. So here's what that code sort of looks like. So the blue here is my input, and the red here is my output. All right. The red is my output. So basically what you can see here is I basically have the differential equation, right? So Vn equals tau dV out by dt plus V out. I basically am taking this, converting it to a discrete time equation, and then simulating it, right? With this value as my input. So notice that I'm applying specifically the input that we just talked about, all right, that we just figured out, which has a 56.3843 radian per second frequency. All right, so I zoomed in real quick on this, right? My goal was for this thing to be a constant, all right? And the goal was for it to get to, in steady state, 2.5 volts. And I see that it looks like it's about 2.5 volts, but it's rippling a little bit. That's the result of the fact that the filter is not perfect, right? So what I did here is I looked at this and I said, all right, so the average is about 2.5, but the peak to peak value of that ripple is about 0.2785 volts, right? If I go back and I look at my predictions with the actual value of h of omega naught, so it said it should have been 0.0564 is the amplitude. All right, so the peak to peak value would be basically 0.1128. So the predicted value was 0.2257. All right, so first of all, what is this? Just to be clear, right? When I say V out of omega naught is, so this means that the amplitude is 2 times that. The amplitude being, remember, if I have alpha 1's magnitude is 0.0564. Remember that the corresponding, C1 cosine omega naught t plus phi, that means that, remember, C1 is going to be 2 times that, right? 2 times 0.064, right? So in this particular case, right, so 2 times that becomes this, and the peak to peak value is always from the bottom to the top. So that brought this to 0.2257. So I said, this is what was predicted. My actual ripple is a little bit higher. And the reason my actual is a little bit higher is because I didn't take into account all the other harmonics that are also in this thing. Okay. All right. There's a lot going on there. But any questions that you guys want to ask about that? I know there's a lot going on, but hopefully the key point, right, is basically how there's two key points, I guess. First is that you understand how to make the graph. And the second is that you understand how to use that graph to be able to essentially create the constraint that we had. So, right, you're figuring out what point am I looking for on that graph, then choosing the switching frequency. If you get that idea, then it's a fairly straightforward thing to do. All right. I know there's a lot there, but it is pretty straightforward once you kind of get that basic concept. Questions about that? There will be some eventually, I suspect. Like I said, I don't. Yeah. So, um, the thing that I mentioned before, so the question about semi-log x. So semi-log x is basically, it's a good question, right? What it does is it makes sure that the x-axis is plotted logarithmically, right? So remember how I was saying, like when I look at this graph here, these points go from 10 to the minus 2, 10 to the minus 1, 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. That's not a normal looking graph. Those values should not be. They're basically equally spaced from each other on that graph. Semi-log x, what it does, right, is it makes sure that that graph is done that way. So I just give it these values of omega that I have, and I say, okay, make the graph on that paper. I tell you when to use the semi-log x command. All right, so that hopefully will help with that. All right. All right. Any other questions on that? How are we doing on time? Yeah. All right. I'll expect there probably to be more as you guys actually try to get through this thing. All right. So a couple of things. I just wanted to walk through that a
I
little bit.
actually have a question
Yeah.
on something you did. Can you
Yeah.
explain where you got that 20 from? Why do we have to multiply the log value of h omega with 20?
That's a good question. That's basically just the definition of a decibel. So I talked about this on Thursday, right? So if I take the log of the magnitude, 20 times the log of a magnitude is a decibel. And it's just a standard way of basically making these things. So it's arbitrary. There is a rationale behind it, but it just gets into the rationale of what the unit of the decibel is, right? So it just tends to be the way we make the graph. It doesn't have to be. You could just do log 10 of the magnitude rather than 20 log 10, but it gets into what the definition of a decibel is, basically.
Okay, thank you.
Yeah. Any other questions? All right. All right. So what I'm going to do is in the rest of the time here, I wanted to kind of go through a couple of things with respect to the other problem. So in problem one, basically, if you go through the parts of the problem, part A is basically, it's a bonus if you can answer this, but basically I tell you, all right, how did I get this differential equation? You need to tell me the differential equation from this circuit, right? That's all that is. So I give it to you. So there's really nothing to do for it unless you want to try to actually derive that from the circuit, which again shouldn't be hard if you know differential equations at this point. Okay. All right. So part B basically is to take these two equations. All right. Now, in this case, I'm not talking about Fourier transforms. Basically, I'm saying take these two equations and turn them into discrete time equations. So basically, part B is to say to turn these into equations where I have VA of n and VA of n plus one, all that sort of stuff, right? So this equation would be part B is to turn it into discrete time. So basically, where everything's a function of n rather than t, right? So you're gonna have two equations when you do that. All right. So essentially, what that means is you're going to get one equation for VA of n plus one. That's going to be in terms of, right, just as a function of IA of n, IA of n plus one, and omega of n. right? The first equation is going to be in terms of those things. The other equation that you're going to get from this guy, you're going to get an equation for the speed where omega n plus 1 is going to be a function of IA of n, omega of n, and that's it. Okay. So basically, you're going to get two equations. That's part B. Part C is to determine the time step. Now, what I tell you to do, all right, when you do this, is to basically look at the two equations and to look at their transient responses. Because remember our thing about choosing the delta t, right? Typically, what I wanted to do is I said if I have these are both first order differential equations. I know it's a little bit strange. I could turn those into one second order differential equation by combining them, but we typically think of them separately. All right. So basically, if I look at this, both of the two are first order differential equations. So in part B, I figured out what the discrete time was. Part C is to determine the time step. So in part C, the thing that I tell you to do is to look at the electrical equation. So look at the electrical equation. That's this one. This is the electrical. And this is the mechanical. We call them that because basically the electrical came from the electrical circuit, the mechanical came from Newton's laws, right? So for the electrical circuit, what I do is I look at that one and I say, well, let's set omega equal to 0. Let's assume the speed was 0. And you could do that. I could basically get something called a brake or a dynamometer, and I could basically hold the shaft of the machine so it didn't spin, right? The machine didn't spin. This circuit works fine. Just means that this voltage source is basically equal to 0 volts. All right. So basically what I'm left with then is VA equals IA RA plus LA DIA by dt. What I ask you to do is to figure out the time constant for this particular circuit, right? So if I turn this into my standard form, right, which is in my standard form, I would say VA over R equals tau DIA by dt plus IA. So you look at that, your tau is equal to apparently L over R, so LA over RA. And what we said before is essentially to see the entire transient, I need to make sure that my delta t is much, much less than 5 tau. Okay. And so basically I have a tau that comes from this one, and then I have a tau that comes from the other one, right? And so if I look at the other circuit there, the other equation, so I have J d omega dt equals K IA minus beta omega like that. For this one, I say let IA equal to 0. And I get J d omega dt plus beta of omega equal to 0. And I look at this and I get a time constant by putting it into standard form like that. So in this case, I have a time constant that's J over beta. So essentially what I'm doing is I'm saying I have two constraints. I have two choices. So choice one is that I want my delta t to be much, much less than 5 times L over R. And then choice two is that my delta t needs to be much, much less than 5 times J over beta. And I give you all those values, right, in the problem. You need to choose the smaller of the two. All right. So basically that's what it's telling you to do in that particular part of the problem. All right. Any questions about that? Is that I'm hoping some of you guys might have actually gotten to that point. All right. Once you choose your delta t, then you're basically solving those two equations, right? So you're basically dealing with these two equations in a for loop again, right? And I think I tell you the endpoint to use. Okay. All right. So the rest of that problem isn't it's something you guys might struggle with, but it's fairly straightforward once you understand really what I'm kind of asking for. So part E, all right, so it says you're going to make a position controller for the DC motor. So if I just as an example here, so if I looked at like a robot arm like this robot arm would be controlled by a DC motor. And so it would spin in this direction. It would spin around its axis, right? So the claws would grip, obviously, but that arm would also spin so it could pick things up, right? So if I want to make a nice version of a robot, what I want to be able to do is I want to control the angle theta that guy can turn through, right? So if I want to turn it 90 degrees, I want to make sure that it turns exactly 90 degrees. So I have to figure out basically in controls, I have to figure out how to make that thing turn exactly 90 degrees. So to do that, I basically make you include also not just, so back to my initial picture, right? I can talk about the speed of the shaft of the motor, but I can also talk about its position, all right? And so the position meaning if I only want to spin this thing 90 degrees, I can talk about its speed, but I can also talk about the position of it. So I talk about the relationship between speed and angle. So in problem one, I also say, well, I want to include the the position as well. So if the position is theta and the speed, so omega is the speed, theta is the position of it. You guys know in a linear system, right? So if I say the velocity is dx by dt, so basically the rate of change of position. Rotationally, I just have that omega equals d theta by dt. Okay. Now, what all I'm asking you to do basically in part D, okay, is part E, is that you add this differential equation to your simulation, which is to say that you would have another equation, theta of n plus 1, which will be a function of theta of n and omega of n, right? So basically, you'll add one more differential equation and you'll redo your simulations. Pretty straightforward what I'm asking you to do there. The harder part is really what I'm asking you to do here. This is where I think the hardest part of the problem is, which is to make what I call a position controller. And I basically say what you're going to do is you're going to design the control system to force the rotor to spin from 0 degrees to 45 degrees, so pi over 4 radians, okay? And I use the radians very specifically in this case because the motor speed is in radians per second, all right? So to create the controller, what I do is I basically have to come up with a way to figure out what the voltage needs to be. Okay. So essentially what this is doing, let me erase this stuff for a second. All right. So how to get through part E shouldn't be too difficult. You guys should be able to figure that out. All right. The hard part is going to be this part F. All right. So what I'm saying is, I want to figure out the voltage to apply. In reality, in the real world, we call this basically feedback when we do controls. I'm saying VA of t is equal to some value. What did I call it? K. So I called it Kp theta times theta ref minus theta of t. All right. This, if I'm looking at the motor, this is the position of the rotor over time, or the position of the shaft, whatever you want to call it, right? This is my desired value. So I said that I want this thing to move to pi over 4 radians. So at t equal to 0, let's say, I might have theta sitting at 0 degrees, and I want it to move to 45 degrees eventually. So what this value does is it says, like if I was actually looking at the motor, so you guys have probably seen this, if some of you may have seen this, if you played with robotics, you would have basically some kind of a sensor, maybe something like a Hall encoder or something like that. Some of you guys may have seen that. Basically, some kind of a sensor that measures the position of the shaft. And based on the position of that shaft, it basically, you feed that into the microcontroller and it changes the voltage that I apply to the motor. Okay. So it changes it over time. So basically what I do in this problem is I say, okay, start out with setting this Kp theta equal to 1, right? set that guy equal to 1, just so that you have a known value. And so essentially VA of t is equal to 1 times pi over 4 minus theta of t. Okay. What I'm asking you to do in your code is to basically, once I'm in discrete time, these would become of n, right? VA of n is equal to pi over 4 minus theta of n. What I'm basically asking you to do is to choose the voltage that I apply based on the angle of the machine. So essentially if you think about it, you're going to have 3 equations, right? You can have an equation for an equation for IA. All right, you have an equation for IA of n plus 1. I gotta be careful. I'm gonna make sure I didn't say this wrong. I said this wrong earlier. I just realized that. Going back a slide here for a second. The electrical equation, because the derivative is on IA, I get a result for IA of n plus 1, right? So just making sure, right? You guys see that. I realized I messed that up earlier, right? So essentially, when you're solving this differential equation, you're always solving for IA at the next time step in terms of VA now, IA now, and the speed now. Essentially, what I would do when I get to this problem in part E, I'm going to have an equation for IA of n plus 1, one for the speed, and one for the angle. And what I'm going to do is I'm going to take the value of the angle right now and use that to calculate the voltage that I apply. And then, so every time I go through the for loop, I'm basically changing the value of the voltage that I actually apply. So essentially, the first thing I would have to do inside my for loop is I would have to calculate VA of n as pi over 4 minus theta of n, right? So I'd make that calculation, and then I would calculate IA of n plus 1, then I would calculate theta of n plus 1, or sorry, omega, and then I would calculate theta. And then I would go back to the top of the for loop again. So every time I go through that loop, I'm basically computing a different value of the voltage. What you're going to see with this, right, when you actually, when everything's said and done and you look at the graph of the angle, right, what you're going to see is that the angle does something like this. And it has this underdamped looking response that ends up at pi over 4 radians. All right. Now, all that I ask you to do in the last part of that problem is to just play with the value of Kp of theta. And I just basically say play with it, adjust it, adjust it downward from 1 and upward from 1 and see if you can get this underdamped type of behavior to disappear. All right. Because again, we talked about this before. Like if I'm controlling something like this, it would mean that if I was looking at the motor, you would see it spin towards 45 degrees. So it would spin past 45 degrees, overshoot it a little bit, and then it would go less than 45 and then more than 45, and eventually it would settle in at exactly 45 degrees. Right. It's not a particularly hard problem if you can understand what's going on here. So basically, you got to get these equations done, right? Then you got to get your time steps using the approach that we described. And then essentially what you have to do is to then include this position piece and then try to take this approach here to make this what I'm calling closed loop controller. And then you'll see this behavior. All right. Without the closed loop behavior, in other words, without this control, what you'll see is the theta of t basically just goes off to infinity because basically the motor just keeps spinning. The angle just kind of keeps increasing forever and ever as it keeps spinning freely. All right. Some of you guys hopefully have tried that already. At least some people have. I'm sure probably not everybody, but hopefully a lot of folks, have been able to try it a little bit by for now. All right. Any questions?
Will you be available over break?
You can try to send me a message. Chance I will definitely have some time to be able to answer some of those questions for sure. All right, Eddie. All right. So, I could go a little bit into one other questions. I will not post the grade ever without giving you guys uh, a physical copy because you'll send me emails after emails after emails about why you got what you got, and I will not do that without giving you a physical copy. So I will post the grades after I give you guys the physical copies on Tuesday. Um, all right. I do have a little bit more that I was going to talk about. I'm prepared to talk about as it relates to problem two. Um, I'm maybe I'll dive into that a little bit real quick in the time that I've got. I got about 15 minutes, I guess, or 12 minutes. But let me go through that real quick. If I look at this, this is the problem that I gave you. Basically, it's again, I'm sort of designing a filter again. All right. And so what I did was I said I have this particular waveform here. I say that this current that I'm measuring, Vs of t, is essentially what is it? It's some 60 hertz waveform. Some 60 hertz waveform plus essentially some other Fourier series. Right? And that Fourier series is this waveform that looks like this if I zoom in on it. So what I'm asking you to do is to try to filter this out. All right. So this particular waveform, if I look at this, what I ask you guys to do is I ask you guys in the problem to basically figure out, so determine the Fourier transform for these values, plus minus 1, plus minus 2, and plus minus 3 using the figure, right, for those values. Now, so that means that you'd have to do the integral again. So what you would have to do is you basically would have to do it so for one period, which would be from here to here. All right, now, looking at this guy right here, what is one period of this thing? Can you guys tell?
Is it just 1 second?
Well, yeah, the reason I wanted to point this out is it has this thing that MATLAB does here. That's this times 10 to the minus fourth. You're right. So it goes from 0 to 1, but MATLAB will do this where it says times 10 to the minus fourth. So it means the period is actually 1 times 10 to the minus 4 seconds. All right. So when you calculate everything, normally when I do you do the integral, I usually do it in terms of t, and then at the end plug in t. But essentially this guy is got a period of 10 to the minus fourth. It looks like 1 second. And so I wanted to point that out. What you do is you'll then figure out, okay, what are the functions over those, what's this line and what's this line, right? And then effectively what you'll have to do is to calculate the values of x of t from the figure. Okay. So you're basically calculating for this alpha n for these values, and then you're turning that into the c sub n. And that's the key thing. I don't really care about the angle. I mean, once you get the alpha values, it's easy to get that. But we're looking, I'm really trying to get you to figure out what those amplitudes are. Okay. All right. So what I'm asking you to do here is to design the filter. So what I did was just the filter being, in this case, Vs is the measured current, and then I'm given the microcontroller a filtered version of that. So basically I have Vs of t going into this filter, and then the output is Vs out, I call it. So essentially what I'm trying to do again is I want Vs out of omega to be right? I get that relationship again. And I do it in terms of the magnitudes typically like that. Okay. All right. So now what I do is I give you a couple of constraints, right? So, and I give you essentially 3 different choices for the filter. What I ask you to do is to basically compare those 3 choices. Only one of those choices is going to meet all of the constraints. So I'm asking you to do 2 things. I'm asking you to choose the filter and then to basically choose this value of omega C. And essentially the way I do this is I look at this and I say, all right, what are the constraints, right? And how do I then test those constraints, all right, using those options for the filters, right? So let's take a look real quick. Constraint number 1, determine a constraint on H, the magnitude of H of omega naught, so that the amplitude of the output signal at omega naught will be 1% of the amplitude of the input signal at that frequency. All right, so let's just see what that means, right? So what we said is the magnitude of the output is equal to the magnitude of the transfer function times the magnitude of the input. Okay. All right, so what's going to happen is you're going to figure out up here what C1 is. C1 is going to be, so whatever it is, it's 2 times whatever the magnitude of the alpha 1 value is. Okay. So essentially what I have here is H of omega naught. If I at omega naught, at the fundamental frequency of that thing, what I have here is that this magnitude, so at omega naught specifically, right? If I look at that particular value, the magnitude of the Fourier transform there is always alpha 1. So what I'm saying is constraint number 1, determine a constraint on the magnitudes of the amplitude of the output signal at omega naught will be about 1% of the amplitude of the input signal at that frequency. So I'm saying is, all right, the amplitude is always 2 times this magnitude. So what I'm saying is I want to ensure that Vs out of omega naught will be less than 1% of the amplitude of the input signal at that frequency. So whatever the C1 value is that you found, whatever that is over 2, right? Essentially, I want to make sure that Vs out of omega naught is less than that particular value. So that will be a number you can determine. So you'll have what the value of C1 is, and so you'll create that constraint. Okay. And then what I basically do is I then basically go in and I attempt each of these particular filters to see if it's possible for me to choose a value of omega C that will meet constraint 1 and constraint 3. So basically what I do is I look at these constraints and I basically go through a process of elimination. All right, now the other 2 constraints I have are on the angle. So I say determine a constraint on the angle at 2 pi 60 degrees if we want the phase shift between the input signal and the output signal to be less than 4 degrees at 60 hertz. Okay, so the other thing is this, so the Fourier result here, so Vs out of omega equals H of omega times Vs of omega. So I keep talking about this in terms of the magnitudes, but this is complex numbers. So I can say Vs out of omega equals angle of H plus angle of Vs. Okay. So angle of H is equal to the phase shift, the shift between the 2. Okay. So I'm saying we want this at 60 degrees or 60 hertz. I want the angle of this guy apparently to be less than 4 degrees. So what my job is basically with these constraints is to go through and to see if if I can then make this happen. All right. The other constraint I have is determine a constraint on the magnitude at 2 pi 60. So the amplitude of the input signal and output signal is approximately the same. So constraint three is that basically I want V out at 2 pi 60 to be approximately the same as the input. So that's Vs of omega, specifically at 2 pi 60. I want that to be the same. That means that I want the magnitude at that particular value to be equal to approximately 1. So what you're going to do in this turns out to be fairly straightforward. Basically, what you'll do is you'll try the first filter. You try H1 and see if you can choose a value of omega C that will meet constraint 1 and constraint number 3. All right. Now, the thing that you're going to find out when you do this, and we'll probably go through this example on Tuesday next week, what you'll see is that you're not going to be able to meet constraint 1 and constraint 3 both with that particular filter. What I'm asking you to do in this particular problem is to go through the design process to try to see how the design should work. Okay. All right. So without having attempted any of this problem, you guys are probably a little bit lost about what I'm trying to say. My suggestion is between now and Tuesday, you guys definitely need to try these problems. All right. I will be, I will be available via Discord over the weekend if you guys want to sort of ask me questions. Definitely on Thursday, it's probably hard for me to be able to answer for sure. But I would, Friday, Saturday, Sunday, I should be able to answer you guys with questions. Okay. All right. That's all I've got. Project 1, I know you guys want to be able to see what your grades were, but you also want to be able to sort of know for how to deal with the report. Certainly you'll be able to take a look at those on Tuesday when I give those back. All right, I'm going to end there. And I can hang on